Okay, well, I want to look at an example problem with you. This one involves the constant cooling. I apologize about the shadows on this paper. I'm not sure there's much I can do, but maybe periodically I can move my hand out of the way. Yeah, but what we want to consider is a rigid tank. Remember, when we hear the term rigid tank, that's telling us one very specific thing, and that is that the volume is a constant. Okay, so rigid tank with a constant volume, it contains water vapor at 250 degrees C and an unknown pressure. When the tank is cooled to 150 degrees C, the vapor starts condensing at at T equals and I should say begins condensing. So the question says to estimate the initial pressure in the tank. So the question is, what is P1? Okay. Well, this puzzle requires a little bit of thought, a little bit of thinking to sort out. So yeah, we don't know much. So what do we know about this process? So we've got two states, an initial temperature and an unknown pressure, and we've got a final state, and that is a temperature and a suggestion that the vapor begins condensing. What do we know about thermodynamic states, specifically the property diagram for a pure substance that changes phase? What phase or phases is present, or where are we in the context of a two-phase region if the vapor just begins condensing? Okay, so think about that for a minute. The vapor just begins condensing. It's all vapor and it just begins to condense. So we'll just begin to see some droplets of liquid appear as it condenses. All right, so that's one thing we need to think about. The second thing we need to think about is what kind of process is this? We know that it's a rigid tank, and therefore the volume is going to remain constant. It wasn't stated explicitly here, but there's no mass that goes into or out of the tank. So we're going to maybe assert an assumption, if we need to, that the mass is equal to a constant. And this seems reasonable given what was described in this problem. So if we assume that m is constant and we're given that v is constant, then it certainly stands to reason that the specific volume, which is the ratio of those two things, is constant during this process. Okay, so if we look at this process on any kind of temperature volume or pressure volume diagram, then it's just going to be a vertical line on that diagram. It can only go up and down, right? So let's just put this in sort of an abstract configuration and just say, let's suppose that we have temperature and volume, I don't know, maybe I'll regret that later, but if we have temperature and volume, then whatever the volume is, V1 equals V2, it has to be a constant. And we do know that if we're cooling this off, then the temperature will decrease. So cooling is in this direction. Okay? So we know that. I mean, just from the way this problem is described, we do know that we're moving from a known temperature, 250 degrees C, to another known temperature, 150 degrees C. And we know that it moves at a constant specific volume. But what is this initial pressure and what is this final condition? If we could find either one of those, I think we can find the other one because we know the specific volume is constant. That can help us find the missing state. But go back to what I suggested earlier as a hint. As this cools, the second state becomes a state where it just begins to condense. So if we think about this in the context of a phase change diagram, what part of the phase change diagram does state 2 fall on? Well, the answer is that it's going to fall on the saturated vapor portion of the line, because that's where we're going from fully vapor, that's saturated vapor. If we go any further, it just begins to condense. Okay, so state 2 is at this boundary that we would call the saturated vapor line, and I'll attempt to draw this into our sketch, that it might look something like this. Remember, this was our critical point here at the top. This is now our state 2, which is on the saturated vapor line, and state 1 is connected to state 2 by this constant specific volume process. Okay, so very key to this process, this problem, is that since at state 2, that tells us that state 2 is saturated vapor. And as we have said before, when we're told that we're in a saturated vapor state, that's a lot of information. If we know it's saturated liquid or saturated vapor, those are very specific places. So what we need to do then is we need to find so how do we find pressure 1? That's the question. We can see the picture, and we know state 2 is on the saturated vapor line. So that means we can find this state. We can find everything about state 2. So if we can find V2, and we know that V1 has the same value, then we can use that information to determine whatever we need to know about state 1. So let me summarize this, that state 2 is completely defined by the property pair T2 and essentially x2 equals 1.0. In other words, it's saturated vapor. State 1 is then subsequently defined in terms of the property pair T1, and V1 is equal to V2. Okay? Oh, sorry, you can't see that information. Okay. There you go. State 2 is defined by the coordinates temperature 2 and essentially quality equals to 1 because we're on that saturated vapor line. And state 1 is defined by the property coordinates T1 and V1 equal to V2 once we find V2. All right, so how do we proceed? We need to go to find VG at T2, and that's going to be equal to V2. Hopefully I can unearth that from some tables. Let's see if I can find it. I hope. Let's see. My goodness, this is small. Okay. Well, it'll be a moment. But let's see, at 250 degrees, I think that the specific volume, oh, I'm sorry, I need 150 degrees. So at 150 degrees, the specific volume of the saturated vapor is 0.39248. 0.39248 meters cubed per kilogram. And hopefully these tables agree well with the tables in your book, that they are from a slightly older edition of the textbook. But regardless, if we now know that, we need to go into the look in the superheated tables. Why am I looking in the superheated tables? Because this property diagram that I've created, the property diagram clearly shows that the state 1 is in the superheated vapor region because of the shape of this two-phase region. So I know it's in the superheated region, and I'm looking in the superheated tables for a place where at the temperature equals to 250, the specific volume is equal to 0.39248. And I'm going to have to do that in sort of an awkward way because the tables aren't arranged conveniently for that. The superheated tables are arranged in these subtables according to pressure, and I'm going to have to scan across the page along lines of T equals 250 degrees C until I find this value in the table, or I find two values on either side of that value at 250 degrees C. So I'm starting, and when I'm looking at, for example, at 20 kPa, the value is 1.19, which is way too large. At 80 kPa, the value is 0.2932, which seems to be too small. So I need to go to lower pressures. At 60 kPa, the value is 39390. So at 60 kPa and 250 degrees Fahrenheit, we find the specific volume is 0.39390. And then the next one down, at 80 kPa. I'm sorry, this is 600 kPa, and this is 800 kPa. 0.6 MPa and 0.8 MPa. and 250 Fahrenheit, I get that the specific volume is 0.29321. And these are both meters cubed per kilogram. Okay, so this is a situation where I'd say, hey, it's pretty close, and if I need to just estimate the initial pressure, what do I mean it's pretty close? Well, this is supposed to be 394, let's say, and I've got 3925. So that's close, but it doesn't hit it exactly. But again, more just to illustrate this interpolation, we could interpolate to get a good estimate. And to do that, we'd put specific volume over here, and the numbers that we have are, and I put pressure over here. So at 600, I'm going to put 0.39390. I don't know this number. And then at 800 kPa, the number is 0.29321. And the value I'm trying to find is 0.39248. Okay, so again, I need to set up ratios of these differences. And so I have to maybe be a little careful because of the signs here. But I'm going to say that 0.39248 minus 0.39390 is to 0.29321 minus 0.3930 as is to 200. 800 minus 600 is 200. Okay, so it looks like we can find this. Question mark is equal to 200 times this ratio, my fraction, plus 600. So I'm going to have to go offline here, see if I can come up with that number. Let's see what I've got. Calculator says 0.39248 minus 0.39390. I need to divide that by 0.29321 minus 0.39390. And so my fraction is 1.4%. So question mark is equal to 200 times 0.141 plus 600. And so that's what I was saying when I was just eyeballing this, is that this number in the table is very close to the value that we have. This fraction is very small. We don't really need very much of an adjustment. 2.82 as a matter of fact. So question mark P1 is approximately equal to 602.8 kPa. Okay, so that's an example of constant pressure cooling, where the fluid condenses when it cools far enough, and we have to use that constant volume process to connect the second state back to the first state.